In this video, we discuss the concept of molecular orbital theory as applied to homonuclear diatomic molecules, continuing with our discussion that we started with the video on H2+. We'll start with some basic definitions. Sigma orbitals, which we introduced in the previous video, will be found to be those orbitals with what we call cylindrical symmetry, meaning that we can rotate these about the internuclear axis and find them unchanged. And more importantly, all sigma orbitals correspond to m sub L quantum numbers equal to 0. That is, the angular momentum with respect to the z-axis is equal to 0 for sigma orbitals. We'll introduce in this video pi orbitals, which do not have cylindrical symmetry and correspond to sideways overlap. And in this case, the m sub L values for pi orbitals correspond to plus or minus 1. We'll also note that when we're adding orbitals together, atomic orbitals and the linear combinations, that we'll only be able to mix orbitals which have same symmetry and similar energies, which means that, for example, the 1s and 2s orbitals will not interact or mix significantly because their energies in most atoms are so very, very different. We'll also introduce the concept of bond order, which we calculate by taking the number of electrons in bonding orbitals and subtracting from that the number of electrons in antibonding orbitals, dividing that total by 2. We will find that the bond order in many cases is very similar to what we would get by considering Lewis structures alone. However, we will find differences, and those differences will be significant. Here is a diagram, an energy diagram of the bonding and antibonding orbitals that we determined for hydrogen in a previous video. We had the bonding molecular orbital and antibonding molecular orbital. The bonding molecular orbital is lower in energy than the individual atomic orbitals, and the antibonding orbital is higher in energy than the individual atomic orbitals. Going back to the diagrams which show us the probability density, or excuse me, the wave function plotted, where 0 on these graphs corresponds to the midpoint between the two axes. We of course have the situation where we've got the 1s plus 1s constructive interference to generate the sigma bonding orbital, the 1s minus 1s destructive antibonding orbital. Those we talked about in the previous video. Now let's move on to 2s orbitals, and we have a similar kind of thing. We have 2s plus 2s bonding orbitals, and in that case we see again that enhancement of electron density in the internuclear region as we did before, and the 2s minus 2s antibonding orbital. No differences here. We're just dealing with atomic orbitals that are farther from the nucleus and will be useful when dealing with second row diatomic molecules. Now we'll consider the situation where we are looking at orbitals with the 2p linear combinations. And in the first diagram here, we see that we have the 2pz orbital overlapping in a cylindrical fashion. So these are sigma orbitals that we're generating. They have cylindrical symmetry. And in this case, we'll notice that there is a nodal point. Now, and again, let me remind you that these are the 2pz orbitals that we have here, that this axis along the internuclear axis is the z-axis. And in this case we get destructive interference in the internuclear region, so this is in fact an antibonding orbital, but it is a sigma antibonding orbital. Here we have, in the next diagram, we have the 2pz orbitals overlapping so that we've got constructive interference. Notice in that internuclear region and where we have the same sign of the lobes of the p orbitals overlapping, so we have constructive interference. This would be a sigma bonding orbital. And again, we'll note we've got this enhancement of electron density in that internuclear region with the maximum at the center. And then we have a situation where we have sideways overlap of the 2px or the 2py orbitals, and in this situation we see destructive interference in that internuclear region. When we look at that overlap, we have this node at the center, and so this will be a pi antibonding orbital, which we'll call pi star. And then finally, at the bottom, we see constructive interference between the lobes above and below the internuclear axis. That's reflected here in this particular diagram, and this would be a pi bonding orbital. Now, we'll note that because we can get 2px orbitals overlapping in a sideways fashion and 2py orbitals overlapping in a sideways fashion, that pi orbitals are doubly degenerate. We'll see that in our molecular orbital diagrams that we draw later. Now, this diagram shows the molecular orbital diagrams from comparing hydrogen H2 to helium-2. The top diagram represents molecular hydrogen, which has 2 electrons. We will fill in those 2 electrons, so we have an electron from the 1s orbital of hydrogen A and the 1s orbital of hydrogen B. We have 2 electrons. They will both go into the lower energy bonding orbital. The bond order of hydrogen is equal to 1 because we have 2 electrons in the bonding orbital and 0 electrons in the antibonding orbital. So using the formula we discussed earlier, we get 1 for our bond order. And of course, our simple Lewis structures for molecular hydrogen would indicate a single bond. So we see a relationship here between bond order and what we would get from drawing Lewis structures. Moving on to helium. Helium atoms have a 1s2 electron configuration, so each one contributes 2 electrons, or total 4 electrons. 2 electrons go into the lower bonding orbital, and then 2 electrons go into the antibonding orbital. As a result of that, when we calculate the bond order of helium, diatomic helium, we get 0, which is an indication that the molecule is not stable. And of course, we know that helium exists as a monatomic in nature. I should add that there have been studies that showed extremely cold temperatures. Diatomic helium can exist, but those temperatures need to be very close to absolute 0. Now, here is a full molecular orbital diagram showing the electron configuration for diatomic fluorine. We'll notice, of course, that we get the 2s orbitals, as we noted earlier, combining to form a bonding orbital and an antibonding orbital. And then we'll get the 2p orbitals combining to form, here is a sigma bonding orbital. All right. And then we get 2 pi bonding orbitals. And again, as mentioned earlier, it's doubly degenerate, as indicated here, because we have overlap with the 2px orbitals to form one of the pi bonding orbitals, and then overlap with the 2py to form the other pi bonding orbital. And then, of course, we also get the antibonding orbitals. Here we have the pi antibonding orbital, and we have the sigma antibonding orbital. You will note that the sigma antibonding orbitals are much higher in energy than the pi antibonding orbitals. You will also note that the sigma bonding orbital here is lower in energy than the pi bonding orbital, which is what we might expect based on our naive notions about sigma and pi bonding. We'll see very soon that there are, in fact on the next slide, we'll see that there are many exceptions to this. So we have to be careful about making those assumptions. Now let's compute the bond order of fluorine based on this particular diagram. we can look at the number of bonding electrons. We have 2 bonding electrons in the 2 sigma, and we have 6 bonding electrons in the 3 sigma and the 1 pi. Then continuing with the antibonding electrons, so that's a total of 8 bonding electrons. The antibonding electrons, we'll note that we've got 2 in the sigma star and 4 in the pi star, so we have a total of 6 antibonding electrons. Using our formula for bond order, we calculate the bond order being equal to 1, and again, that's consistent with our notion based on the Lewis structure that diatomic fluorine is a single bond. Now in this diagram we see the molecular orbital structure of diatomic nitrogen, which of course we find that diatomic nitrogen contributes 2 electrons each from the 2s orbitals, so there are a total of 4 electrons that go into the sigma g and the sigma u star, and then from the 2p orbitals, nitrogen has a total of 3 electrons in the 2p orbitals, so there are a total of 6 electrons which fill up the pi orbitals and the sigma orbitals. Now you'll notice here in this case the pi orbital is lower in energy than the sigma orbital. And the reasons for this are somewhat complex, and it's because that we are actually allowing mixing of the sigmas, the p sigma orbitals with the s sigma orbitals that changes their energies. We'll come back to that on the next slide. We'll look at how those energies change as we move across the second row of the periodic table. But in any event, for molecular nitrogen, we'll notice that we have this particular electron configuration. If we wish to write this electron configuration out, we'll find that we've got a 2 sigma G with 2 electrons, a 2 sigma U antibonding, and again the asterisk means it's antibonding, with 2 electrons. We've got a 1 pi U. You notice the pi bonding orbital is Ungerada, and we've got 4 electrons there, and the 3 sigma G has 2 electrons. So there is our electron configuration. Of course, this only includes the valence electrons of molecular nitrogen. We're not including the core electrons, which are not significantly involved in the bonding in this molecule. If we want to calculate the bond order, we'll see that we've got a total of 2 plus 6, 8 bonding electrons, minus 2 antibonding electrons. We work that out, and we find that we have a bond order of 3, which is consistent with the triple bond that we get when we draw the Lewis structure of molecular nitrogen. So again, we're seeing some consistency here. This diagram shows the energy level structure for the second row diatomics, starting with lithium and moving all the way across the second row to fluorine, and shows the relative energy levels of these molecules. It's important to note as you go from lithium to beryllium, it also shows their electron configurations. We can calculate the bond orders for each of those. For lithium, the bond order is 1. For beryllium, the bond order is 0. For diatomic boron, we have a bond order of 1. For diatomic carbon, we have a bond order of 2. For diatomic nitrogen, we have a bond order of 3. For oxygen, a bond order of 2, which again is consistent with our drawing of the O2 molecule. We show a double bond. And for fluorine, we have a bond order of 1. The other thing that's important to note as we go across here is the relative ordering of the 1 pi U and the 3 sigma G orbitals. That from lithium through nitrogen, we'll note that the pi orbitals, the degenerate pi orbitals, are lower in energy than the sigma orbital. On the other hand, when we get to O2, we'll find that the sigma orbital actually is lower in energy than the pi orbital, which is also the case for diatomic fluorine. Now, it turns out that one of the great early successes in molecular orbital theory was predicting that O2 was paramagnetic. If we go back and we look at it, I'm just drawing the diagram here again, look at the electron configuration amongst the 2p electrons of O2. What's important to note is that I've got 2 electrons here that are unpaired in the pi antibonding orbitals. The unpaired electrons means that O2 should be paramagnetic. If we compare this to the simple Lewis structure of O2, we would predict that we'd have a double bond with all the electrons being paired. So the Lewis structure diagram predicts that O2 would be diamagnetic. In fact, O2 is paramagnetic. It is drawn into a magnetic field. And again, this shows the relevance and justification for molecular orbital theory description of the properties of molecular oxygen. This table just shows how we write electron configurations for various diatomic molecules, as we talked about before. I will note there is, of course, an error in this table, and that is that term for diatomic beryllium should be 2 and not 1. You'll notice that also the way this is written up in this table is slightly different. The notation used for molecular orbitals is different from what's in your text. Again, there are different notations in different texts. If we go on to diatomic carbon and write out the electron configuration, we'll get that. And this is, of course, the notation that that's consistent with what we have here in this particular table. By the way, this is not diatomic carbon, this is diatomic boron that has this electron configuration. So this ends our discussion of molecular orbital theories applied to homonuclear diatomics. The next video we'll talk about molecular orbital theory as applied to heteronuclear molecules.